Hi, and good morning. Thank you for getting out of bed and coming first thing in the morning. And as they said, this is Where's Waldo's brothers and sisters, and let's talk about some variant analysis. So they already did a great bio for me that made me sound way cooler than I could ever make myself sound. But yes, as they said, I am a security researcher on Google Project Zero. But I'm taking a little bit of a different approach than maybe what you've heard and seen Google Project Zero doing for the last couple of years. My role is I'm focusing on the 0 days used in the wild and seeing what we can learn from them, and then pivoting that to how do we make 0 day hard. So with that, my Twitter is Maddie Stone because of OPSEC is a good thing, right? And yeah, that's me. So let's get to the actually interesting stuff. This is what we plan to cover today. So first, to set some groundwork, what is variant analysis? Because there's a lot of different approaches and thoughts we can all have when we think of that term. Next, I'll share with you why I think it's important and worth y'all coming in at 10 a.m. to come and hear about. Next, we'll get into some case studies. So practically, what does this look like? We'll cover 3 different 0 days that have been used in the wild in the last couple of months, and I'll talk about our methodology for doing variant analysis, the results from that variant analysis, and the lessons learned, which to me, I think are usually the most important and what we can learn the most from. But first, what is variant analysis? So I'm going to use an example. Where's Waldo? You know, children's picture books that have a lot of these crazy scenes, and you need to find Waldo in this before you move on to the next challenge. I've heard in Europe they call it Where's Wally, but yeah, in the US we use Waldo. So you scan and scan, trying in these super busy pictures to find Waldo. And you do. There he is. You're super excited, and you won, you found the thing, and you want to move on. But what if there's more Waldos in there? What if you happen to be in the book where there are multiple Waldos on each certain page? You found one and you moved on, and you didn't use the information you had to continue looking. And what if it's not even a carbon copy another Waldo? But what if Waldo has brothers, sisters, friends who are like him and also need to be found? So in that picture, if you looked closely and kept scanning, you'd also find the character known as Oddlaw, or Waldo backwards, who is the villain version of Waldo, I have learned. And so it would have been much, much easier to also find Oddlaw if we took the time to continue scanning. We know Oddlaw likes to try and track and trick Waldo, so he's probably going to be in the same vicinity. He has similar characteristics in shirt and hat, and so we can use that information to also find Oddlaw. So that's variant analysis to me. We find a single bug or vulnerability, and we use that characteristics and that information to then find other vulnerabilities based on that single one we have. We don't just say, it's all good, done, move on, we found that one bug and fixed it. But why do we care? Why is this important? Because as we all know, one of the most precious resources that anyone has on a security team is their engineer or their professional's time. No one has enough. We all have plenty to do, and not enough people to do it. So first, why do we care about variant analysis? Is that playing whack-a-mole, which is the game where a mole pops up, you use a hammer and you whack it, it pops up a different place and you whack it. If we keep doing that one by one for each vulnerability, we will never be able to handle them all or secure at scale. It's not sustainable and it's not efficient. But if instead we came up with a solution to just say, hey, no more moles are able to pop up out of any of these holes, that's obviously a lot more efficient. And also, if we think about this from the attacker mindset, especially when we're talking about vulnerabilities that were used in the wild, so they were actively exploited against users, is that researchers are often finding more than one vulnerability at a time. They're looking through a set of code that might not have been audited to begin with, so they find a couple of different issues since they're living, breathing, eating that block of code, so they have a few. They learn a pattern that then they can quickly scan a whole code base for, so they find a couple of different places that pattern exists, etc. Attackers are generally using the exact same process and skills that researchers are using to find these bugs. So it's pretty safe to say that if researchers continue to find more than one bug at the same time, attackers can too. And we're making it so much easier for them to continue to exploit if we're only addressing the one we see in the wild. Because then they have others they can plug and play into their exploit with very little resources they have to put into it. And the whole goal is to make zero-day hard. That's always been Project Zero's mission. We're just now trying a different take on it with my role there. And so we want to make sure as an industry that in the failure case, when attackers have had one of their zero-day exploits detected, and we have the opportunity as security professionals to learn as much as humanly possible as we can, we really take that opportunity to go ahead and kill as many bugs as possible. We come up with solutions across the board to try and fix them instead of just addressing the single one. So hopefully I have made my case for why this is worthwhile, but let's talk about what this looks like in practice for 3 different 0 days that were used in the fall. So the first bug we're going to talk about is an Android binder used after free. It has CVE number 2019-2215. So first, to level set, what's this bug? It is a use after free in the Android binder driver, so in the Android kernel, where due to a poll handler using a wait queue that is not tied to the lifetime of the file, there is this use after free. So to break that down another few levels, if we think of drivers, especially in the Android and Linux kernel, basically you have operations being performed on a file. The poll operation is using a structure that is not tied to, that cannot be confirmed it's always alive as long as that file is alive. So that's the nitty-gritty of what this bug is. But there was another important aspect of this that we need to consider when we consider how to approach variant analysis in this case. So this bug was actually patched in the upstream Linux and Android kernels about 18 months prior to then me finding and reporting it based on use in the wild, and it was discovered by Syscaller in November 2017. And I mention this because as we're going to talk about today, I think there's a lot more than just the technical details we need to be considering when we consider our variant analysis approaches. So these are the approaches. There were 2 different ones. The first one is related to how was this bug found? Because as we mentioned, not only are there technical details to consider in variant, sometimes the researcher may find bugs that aren't related to the same technical details, but it's in the same block of code, or can be surfaced in the same way that they found the other one. So the first approach is looking for bugs that were patched in the upstream kernels, but were not patched in already launched Android devices. And what I mean by that is that they're patched in the Linux kernel or Android common kernel, but if they are not marked as security bugs and do not make it into an Android security bulletin, then OEMs do not know that they need to patch that and issue a patch or update for the issue. So that was the disconnect of which devices were affected by this issue to begin with. So this issue that was exploited in the wild, it did affect Pixel 1 and Pixel 2 devices, but not Pixel 3 devices. So I decided one of the variant analysis approaches was to diff the Pixel 2's patch history for the binder driver with the upstream Linux kernel's patch history for the binder driver to find what other bugs may have been missed. And that's that variant analysis approach of focusing on process. The second thing is that That's still, even though it's doing variant analysis, it's still a piecemeal approach. So if we take a step back and think of variants, how do we try and kill all variants in this? And that would be a systemic issue of there is a way to find bugs that are patched in the upstream and don't make it downstream to devices. And so that's where, to address those types of variants, I and others on the Project Zero team engaged with the Android teams about how do we do more syncing with the upstream kernel so that these issues as a whole can't happen. And so Android did step up. One thing that was happening and we learned is that one of the reasons Pixel 3s were not affected was that they had already instituted new upstream for all devices. I think that's the P devices, had already had new upstream syncing requirements. And a month after this issue, Android published new advice and process information for how all OEMs should be and can be syncing to upstream more often. The second approach is in the nitty-gritty details of, the technical details of the bug. How do we look for any of the drivers that are in the kernel whose pull handler may use a wait queue that could be freed prior to the file being freed? And so for this, what this means in practice is that here we have the binder pull function from the binder driver. So this is what's called whenever you want to call pull on it. And what you will see in here is there is the call to pull wait. The first argument to pull wait is the pointer to the file struct for this file operation. The second is the wait queue that you are using to give to the pull handler. So what we see is in the first line of this function, it's telling us that the file pointer, aka the file we're performing this operation on, is the binder proc struct. However, the wait queue that we are sending to the pull handler is in the binder thread struct. The binder thread struct can be freed independently of the binder proc, and that's what led to this use after free. So I first went through the Linux 4.4 kernel, because that's what the Pixel 2s were based off it, and I searched for any file in the Linux kernel that had calls to pull wait. Then I manually went through 214 of those 236 files, checking to see whether or not the wait queues that were being passed to pull wait were tied to the lifetime of the file or could be independently freed. Why it's only 214 out of 236 is there were a batch of drivers that were not actually used anywhere or not tied to the ARM64 architecture. So the results of this variant analysis was CVE 2020-0030, which is called a potential use after free due to a race condition in the binder thread release. And so this is the same exact function that the other use after free was in, because it turns out after they implemented the patch in the upstream Linux kernel for the original binder bug, syscolor found that patch introduced a new use after free race condition. So syscolor once again found it, implemented the patch in February 2018, and so upstream was fixed, but downstream was not. Oops. So that shows us that, there are variants that are associated with process that we need to be finding. And so what that patch, though, looked like is you could see in the Android upstream kernel is if this top code of, I know it's going to be hard for y'all, is they added case checks before they called wake-up calls, so they would call pull free before they freed the thread. Now they implemented a call to synchronize RCU to make sure there was no race condition there. And this is what the race condition was, is that if you tried to delete a binder thread through the ioctl binder thread exit while also calling epull ctl del, then there was an opportunity that you could free the thread when the wait queue was included or is embedded in the thread struct, and yet it would still be used again in the same place as the original use after free here. So that's what that race condition looked like. Thankfully, Android patched it on Monday in the February 2020 security bulletin, so thank you to them for patching that. So the second approach, going through all of those different driver files, found one place that looked like it potentially had the vulnerability, where the weight queue that was being passed to the pole weight handler was not tied to the lifetime of the device. But when I started digging into it to try and write a proof of concept, turns out that that driver had been used in one single device for a single chipset that was then deprecated and no longer used, so didn't follow up. But all the other drivers in the Linux 4.4 kernel looked good. But lessons learned. So I think for me, especially as one of the first cases of going through this in a very deliberate manner, was that, one, we have to be thinking about variant analysis more broadly. Each time I hear about variant analysis, it's usually about the bug class, the exact details of how the bug technically works. But there are so many other types of variants we need to be considering. And some of the easiest ones for researchers to find are going to also be in the block of code that they're already studying, as well as things that are surfaced by the same process. So the next point is that all of us have said this till we're blue in the face, and so I'm not saying anything new, but it keeps happening. We need to be pushing downstream products to be syncing to upstream more regularly. This case was even shown in a recent pwn to own when some of the Android browsers were pwned by vulnerabilities that had already been patched in the upstream Chromium. So they were known, but they didn't sync, so those vulnerabilities still worked. Lastly, I probably should have done static analysis instead of manually looking at 200-something different drivers, but I didn't. I was in that tunnel vision focus, and so sometimes we need to take a step back and remember that was probably not the most efficient. There are ways to do variant analysis in efficient and more productive ways. So that was case study number 1, the Android binder bug, and now we're going to move to a whole different platform. This one is a Chrome use after free in the web audio module that was disclosed and fixed at the end of October of this year. It has the CVE number. So what's the what's the bug? It's use after free in the web audio component, specifically the file convolvernode.cc, and that's within the Blink renderer. And it enabled remote code execution within the renderer. So the general issue, which we'll get into in more detail, is that members of a structure are used in 2 different threads, but only one of the threads actually takes a mutex. And so this was discovered by Kaspersky, and they did a great blog post of it, and Boris Lauren, who we get to hear from today, is one of the discoverers of it. So, more details. What is the bug? The use after free is caused by 2 different threads, the main thread and the audio renderer thread, operating on the same convolver node members at the same time. So in the main thread, what we have is if you call set buffer, then the reverb member is freed. And so that's what this code is, as I don't stand in the middle of it. What we have is we have set buffer, which is run in the main thread of Chrome, and then, or in the renderer, and we see at the beginning of this that there is a code path where they will free the reverb member as well as set to null the shared buffer. Oh. And there's no mutex taking anywhere in here. But then in the audio rendering thread, which can be triggered through the start rendering call, and that ends up calling the process method, it uses reverb. And so here's the audio rendering thread call. And the first thing we see is that it does take a mutex. And this is with a code that should have also existed in set buffer. And then it uses reverb process. And so it looks like it should be good because you see a mutex taken and then it operates, but the problem is that the other side does not, and thus we can use this after it's been freed. So that's the variant analysis approach. My wonderful teammate Sergey Glazunov was the one who took the lead on this variant analysis, and I tagged along, and he gave me the great feedback of, if the vulnerability can be described in a single sentence, that makes it a great candidate to use SEML. What is SEML? It's also, I think they sort of rebranded or renamed as CodeQL. They were acquired by GitHub, which is a part of Microsoft. So it is a static analysis platform where you can write queries to look for certain patterns in a source code database. So what we did is write a query to search for instances where there is a member variable used in 2 threads, but the mutex is only taken in 1. So that's what we mean when we say the bug can be described in a single sentence. It's a simple pattern, and so that makes it much more simple to write the query for it when you can describe it like that. And so the query was run over the web audio module, and it found 23 total results, which is great when you consider a static analysis tool because you can really, that's small enough you can go through to see which ones are true positives versus false positives. And in this case, there were 3 true positives found, all within the Panner handler class. And so this is the Project Zero issue on our tracker, 1963, and CVE that. So what he wrote in his report is that unlike in the original issue, the main thread function acquires a lock before changing the Panner pointer, but tail time, as well as latency time, and requires tail processing, which are called on the audio thread, don't. And so he went on to explain to help the triagers understand it, is that usually when you're calling code through the audio thread, they rely on taking a mutex through the process function. However, these function calls did not go through that and could be called through other call paths. And the other thing to note is we sort of have variants of variants here, which we will come back to and talk about. So CVE, this was patched in Chrome 79 in December release. But that wasn't the end of the story. Because unfortunately, after this was released, when Sergey was looking at the patch, he found that it was not complete. When he had reported the 3 different functions that were variants, his POC, though, only called them through 1 path. And the patch that Chrome issued only covered that single path that was in the POC. And instead of patching in each of those 3 functions, they went to the 1 function above that and patched it. So there was still another path into those that did not take a mutex. Oh, yeah, I said it. So they patched 1 code path to those 3 functions, but not the other. So Tuesday, and really cutting close with presentations and really hoping everything was going to go right, in Chrome 80, they did do the fix, so thank you to Chrome for that. But there's a lot of lessons learned here. And this Chrome, although they are the focus of this one, they're not the only way we see it, and this is why they're really lessons learned, is because we're seeing a lot of these same behaviors from vendors across the ecosystem is not quite, but across the world. So 1, vendors are under a lot of pressure to get patches out quickly, especially when we're talking 0 days in the wild. It's a 7-day disclosure date. It's hard, but what that's meaning is it's often leading to poor patch quality, or not complete for the bug at hand, not complete for all variants, and that's leaving a lot of openings. Because the original attackers already know about that single vulnerability, and of course they're going to double check what your patches did. And if they already know the details of their vulnerability, it's going to take a very minimal amount of time for them to pivot and then cover the other ones, or use the other ones. Also, what we find a lot in Project Zero bug reports is that vendors are patching to the proof of concept, or POC. They just make sure the POC you submit doesn't work even if you call out that there are other variants in addition to the POC. And this is hard from both a researcher and a vendor standpoint, because the POC is a great way to know, did I fix it? It's easy, you run it, especially if you're moving fast. But from a researcher point of view, it's also hard, because how do you write the code for every single type of variant or code path that something could go through? Like, I don't think Sergey expected Chrome to try and patch a level above the function calls he'd mentioned. I think he would expect them to be patched. But then Chrome saw another opportunity. So I think what this means for us is, as researchers submitting bugs, it's good in a POC to specifically call out in the report, hey, this POC is written for this, it will not test, and you need to look into X, Y, and Z as well. But one of the cool things is, I don't know if in your realms as well, static analysis can get a really bad rap among researchers, especially for its sound-to-noise ratio. But in this case, it worked well. And I think a couple of the reasons why it works so well is, one, only using it for a case where you could clearly define what the bug and what the pattern you're looking for is, and second, running it over one module on the time. So instead of running it across all of the Chromium database, we ran it over web audio module, then each other module by itself, which makes the results much simpler to sort through to figure out true positives from false positives. So that's our Chrome case study. For the last one we're going to wrap up, it is a bug that is in Internet Explorer's Jscript. And so it sort of has two different CVEs, which I'll talk about as we cover this. So first, about the vuln. It's a bug class where a Jscript variable, which is represented as a var struct, isn't properly tracked by the garbage collector. And so I'm going to go through a whole timeline of this bug class. In January 2018, multiple bugs were reported from Project Zero to Microsoft about this bug class. They also open sourced a fuzzer to find some of these types of bugs. In December 2018, TAG, Google's threat analysis group, discovered a first bug of this bug class used in the wild. And remember, that's 2018. When I've tried to run this, people thought 2019. We'll get there. So this bug could not have been caught with the fuzzer that was open sourced because it used Jscript features that hadn't been implemented in the fuzzer. Next, in September 2019, there was another detected use of a 0-day in the wild using this type of bug class. And this was, in this case, there were function arguments that weren't being tracked by the garbage collector during the array.sort callback. And so this is the bug we're focusing on as the original bug for this variant analysis. And so it, again, was discovered by Clement from Google's threat analysis group. But what complicated this was the fix was then incomplete for the bug when it was reported and disclosed under the 7-day in the wild. So it was then fixed again under this other CVE number. So Ivan Fracic from our Project Zero team led the variant analysis on this, since he knew this bug class inside and out. So he took two different approaches to doing variant analysis for this bug. The first one was manual analysis. He knows this bug class very well, so he went through each of the different Jscript callbacks that he knew about and manually attempted to free function arguments in each of them. Then, once he'd done that and he still wanted to be really sure about whether there were any other variants, he created a fuzzer to try and find these. And he modified the Jscript DLL such that freed vars were modified so that any access to them after they were freed would crash immediately. And he also made sure that no freed vars would be allocated again. So the results of this variant analysis is he found another bug during the manual review, which is a pretty trivial variant in that members of the arguments object aren't tracked by the garbage collector during the toJSON callback. And so everything is exactly the same as the original bug that had been used in the wild, except it's the toJSON callback rather than the array.sort callback. He then, when he ran the fuzzer, what it found was two different results, which were just the original vulnerability, and then this new variant he had found manually. So it gave some confidence that this was pretty complete, but also that they're variants. Thank you to Microsoft. Both the fix as well as the variant were patched in the November 2019 update, grouping them both under that CVE. So lessons learned is more variant analysis on bug classes when they're originally reported. So each of these different changes in use in the wild were pretty straightforward in the sense of what is this bug class. It's not tracking arguments through the garbage collector in callbacks. And so that really gets into variant analysis, is I know that resources are slim, but when we learn about a new bug class, when we find a new vulnerability, to take a step back and think, how do I address this comprehensively? Do I have options of how to address this comprehensively so that it's not a one-by-one type of thing? Quality and complete patches. The 7-day deadline is hard, it's short, but that's because people are being harmed by exploit use in the wild. And so we need to make sure that in these cases where attackers already knowing about them, they already have the tools built to use them, that we make sure all of our patches are of good quality and complete for even just the bug that's in that exploit. And this one was hard because the bug wasn't fixed initially, and that could have been due to triaging incorrectly, or what, but it also led to a pretty trivial variant wasn't patched either. And if we can find that quickly, that means people who are already using it can find it probably even more quickly. And lastly, one of the things that could help both in the Chrome case and at Microsoft is if vendors can use researchers who are reporting to help come up with patches, because the reporter of the variant generally knows, or reporter of the initial bug really knows that bug and is reporting it because we all want them fixed and protected and things like that. And so I know right now it's tough, but if we can as an industry continue to grow such that we can share patches back and forth, then before it's what's launched to users, the researchers can help vendors know, is this complete and is it actually going to fix the problem? Or maybe we get this one out and then quickly try to release these other couple of fixes that can address issues more comprehensively. And, oh, yeah, I kind of said this. But when things are in the wild, we need to try and reduce this line often between researchers and vendors. I think it's helped that 6 months ago, I joined the Project Zero team coming from working on the Android security team. And so, believe me, I know it's hard from a vendor point of view. And I worked on the preloaded app side. So we had 1,100 different OEMs trying to vet and ensure all of their pre-installed apps were secure. And I think that background has helped to know that we're all trying to achieve these same goals. So if we can use each other and work together, that makes all of these products better and more secure to help keep people from being harmed. So with that, I have a couple different takeaways that I hope can get across. Is first, there are a lot of different techniques for variant besides just looking at jumping ahead. There are lots of different techniques we can use for doing the variant analysis, manual analysis of reversing, source code auditing, things like that. Static analysis tools have shown to be successful the more that we're using them, and GitHub Security Lab, based on Twitter, seems to be having some good results with their code QL queries too. Fuzzing is another option that tends to work out well. I looked through patch dipping histories and change logs, so there's lots of different ways to approach variant analysis, and I would encourage each of you to think of which approach fits your need best. If we take a step back and consider what are these variants that we're trying to find, and then decide on the approach, I think that is what turns out the best. And lastly, as I was saying before and jumped ahead, let's think about both the bug class and the details, the technical details of what is this bug, along with the other aspects that can make it a variant, such as how do you find it, where is the code located, and things like that. So some of the takeaways I hope you have, or my goal for the presentation, was that patching to a proof of concept is not sufficient. And I know that's easy, especially when you're bogged down and you have a million things on your team's to-do list. But it often will not be complete because the POC is going to be one example of showing this bug exists. Also, many times there are trivial variants identified when doing variant analysis on 0 days used in the wild. To be honest, these were the first 3 times we employed variant analysis since I joined the team, and all 3 of them showed results in other variants that we found. So I think that's important. Yes, it's still a small sample size, and I hope to give y'all more data as I'm on this team later, but 3 out of 3 of 0 days used in the wild had variants still in their code bases. And it's important. The attackers have the resources and are finding them, so even if we are resource constrained, we have to remember they're not, so how do we protect people? So let's break it down, because we have a lot of different ways that we can address this problem. First, if a security researcher, what can you do? And one is that I know as researchers, we're ready to find that next bug. It's exciting to report. We want to move on. We're done looking at the thing. But let's check the patches for the vulnerabilities we report. Hopefully, we can continue to grow our relationships with vendors such that they'll share them easier. But even if they don't, you know this code, you know this bug, so if you can go through and check the patch after the vendor has released it and then continue reporting the new bug, let people know the patch isn't fixed, work with the vendor to get it actually fixed, that's continuing our process and not leaving early and leaving things out there. Next, we need to hold vendors accountable for variants. We need to look for variants. We need to ask them why they're not being fixed and things like that. And I think one of the important things we can do is really engage from our side. Help the vendor understand how we found the variants or the bug and not just what it is. Because that process cycle just gives them more and more information. And from my experience, vendors want that. They want the extra information so that they can choose how to act and use it. Because most of the time, everyone wants to fix things and do the best job they can. And lastly, propose ideas for what comprehensive fixes can look like, no matter how outlandish it may seem, because you never know what they may be willing to do, and if you put that out there, all they can do is decide not to use it, but at least you gave them options they might not have thought about of how to kill the bug class or fix things comprehensively. Vendors, what can vendors do in this? As vendors, I was going to say we. I guess I'm not a vendor anymore, but it feels more familial, so let's do it. As vendors, we need to be taking all the information we can from the single vulnerability and use that to then try and make all of our code more secure and not just try to cut time, cut our solved numbers up in those type of metrics as quickly as possible. We need to think and brainstorm with our team members and others, how do we fix this comprehensively? So a week, a month of things down the line, we're not doing the same exact thing again. Vendors can engage with researchers. It would be really great to share patches or share ideas of how to patch earlier, and it saves everyone time because you'll know even earlier before launch if this isn't going to work instead of waiting for the launch and then suddenly getting more bugs filed with you. And I know sometimes it feels like you can't meet a disclosure timeline, but that's not an excuse to stop. Even if you can only address the original vulnerability in the 7 days or whatever timeline, that doesn't mean it's time to walk away and we're done and we close that. We still need to keep working to address those variants because other people will. So what is Project Zero doing? We are working with some of the vendors we report most often to engage, to review, and suggest other options for methodologies and implementations, trying to just do more engagement on that, because fixing earlier is easier, cheaper, and better for all users, which is a pretty big win-win. Next, you might have seen early January, we published a new disclosure policy, which we're changing our focus from just getting a patch out as quickly as possible to also having a focus of quick patches, complete patches, and quality patches. So this is from a table of comparing the previous disclosure policies from 2019 to what we're testing in 2020. It's up on our blog. Give it a read if you're interested. And so one of the things I'd like to highlight is our policy goals of what the disclosure policy were. And that's what I just said of previously the 90 days timeline and releasing the issue right after the patch. Its whole goal was to get the industry to more quickly release patches for vulnerabilities. But we've added a few more goals based on what we've learned, and that's thorough patch development, so things that fix the underlying vulnerability and aren't a misfix, as well as improving patch adoption. But the thing about variant analysis that has changed in this policy is that incomplete fixes and variants weren't explicitly explained of how we would handle them in the previous policies. But as the team has continued to move, we've seen this is a huge issue that is happening over and over and over again. So now what the policy states is details of incomplete fixes will be reported to the vendor and added to the existing report. So in the Project Zero issue tracker, it will be commented that it's an incomplete fix, and it won't receive a new deadline. So if in the 90 days, a vendor A releases a patch on day 50 that actually didn't fix the vulnerability, we will let them know, annotate it in the issue tracker, but there's not another additional 90 days associated with that, because for users, we gotta be fixing these things correctly. And so with that, thank you. I appreciate y'all staying and talking variant analysis with me. As I said, this is my role of focusing on 0 days in the wild is a new role, and it's one of those things that really requires collaboration across the spectrum, from organizations who are doing detection and threat intel to the vendors and to us and who are trying to learn as much as we can as these about the detailed vulnerability being used in those exploits. So please reach out, Maddie Stone on Twitter. I'll be hanging out today. Love to talk to you, and thank you.